Okay, so yesterday we learned about parametrics. Today we're going to learn about the calculus of parametrics. It is time to BOTC. Bust out the good stuff, the calculus, okay? So here it is, in the box. You know, if it's in a box, it's probably pretty important. So if a smooth curve, there you go, nice and smooth, call it C for curve, is given by the equations, the pair of parametric equations, x as a function of t and y as a function of t, then the slope of the curve at that point is, we're still interested in dy dx, because we're still graphing things on the coordinate plane, y in terms of x, like we did yesterday. But here's all you have to do. You take the derivative of y with respect to t and divide it by the derivative of x with respect to t. And of course, dx dt can't be 0. So why does that work? Well, pretty easy to see. You could treat those as individual quantities, so dividing by a fraction is the same as multiplying by its reciprocal, and you essentially have the chain rule working there. Your dt's divide out. So an easier way to think about it is this. dy dx is just y prime of t over x prime of t. So we're taking two derivatives and we're dividing them instead of just doing one derivative. Pretty easy. Now what about the second derivative? The second derivative is a little bit different, okay? You could follow that all the way through, but here's essentially what it is. When you take your first derivative, you're going to have it as a function of t, not x. So the second derivative is the derivative of the first derivative with respect to t, but then you have to divide by another dx dt. Every time you take a derivative, you're dividing by dx dt. All right? So it's the derivative of what you got divided by another dx dt. And this is the part in the bottom that a lot of people forget to do. And by a lot of people, I mean not y'all. Right? Okay. Let's go ahead and try it out. Without a calculator. Okay, cool. Without a calculator, given that x is 2 square root of t and y is equal to 3t squared minus 2t, find the first and second derivatives. And then evaluate it at 1. All right. So because we're going to need the derivatives, let's go ahead and get our machinery up and running. So x, you could write it as x of t if you want. That's 2t to the 1/2. And so its derivative, x prime of t, or dx dt, whichever one you prefer, is going to be equal to what? T to the negative 1/2. Yeah? It's the same as 1 over the square root of t if you want to simplify it. All right, let's go ahead and get our second piece up and running. Y prime of t, we don't have to rewrite it, just using the power rule, is 6t minus 2. So now that you have your two derivatives set up and ready to go, now we can answer the question. So the derivative of y with respect to x is, remember, y prime of t over x prime of t. And you don't need to show that step right there. You do need to put dy dx. So our dy dt was 6t minus 2. And we divide it by x prime of t, which is 1 over the square root of t. And you're essentially done, but I'm going to clean that up a little bit. If I multiply by the reciprocal, you're multiplying by the square root of t. And from there, if you want, you can even distribute the square root of t, which is t to the 1/2, and get 6t to the 3/2 minus 2t to the 1/2. So a lot of different versions of it. So if you were just looking for the first derivative, probably the easiest one to evaluate would be that one there. So let's go ahead and evaluate it now. It says we need to evaluate it at 1. So here we go, using the right notation. dy dx evaluated at t equals 1. That's how you show it in Leibniz form, equals. So again, as I mentioned, that one right there that I highlighted is probably the easiest one of the versions we have up there to evaluate. So if I plug in a 1, I get 6 minus 2, that's 4, times the square root of 1, which is 1. So there it is. So that's the slope of the tangent line at that point. Slope of the tangent line. If you were to just plug in the 1 individually to the numerator and denominator, you would get the component velocity vector. So if you plug a 1 to the top, you get 4. So at that moment, the particle that's traveling along the smooth curve in 2D space would be be moving up vertically by 4 units per time. And then the denominator's evaluation would be 1. It's moving horizontally to the right by 1 unit per time. Okay? But when we divide them out, we get dy dx. That's the slope of the tangent line there. It's 4. Okay, the second derivative. So here we go. The second derivative of y with respect to x is just the derivative of dy dx. So I'm going to go ahead and write that. It's the derivative with respect to t, right? If you look up here, it's the derivative with respect to t of dy dx. And then we have to divide it by another what? Yeah, dx dt. So here's what's interesting about it. Our derivative of y with respect to x is a function of t. So all we need to do to get the second derivative is take the derivative of that. So that's why I went ahead and distributed so that we can use the power rule instead of the product rule. So let's see, 6t to the 3 halves is going to be 3 halves times 6 is 9. So we get 9t to the subtract 1, you get a half. And then the derivative of the second term is going to be minus t to the negative 1 half. Now, a lot of people, not y'all, would stop right there. And if this is a multiple choice question, that's an answer choice. And you take it and you get it wrong. We need to divide it by another dx dt. Okay? And that is going to be 1 over the square root of t. So it's the derivative of what you got with respect to t, and then divided by another dx dt. And if you want to see that, why that works, you could follow the chain rule all the way back to the original one. Okay? Now let's clean that up, because there's another version of it. That's 9t to the 1 half minus t to the negative 1 half. And then if I state change flip, I'm multiplying by the square root of t. So that's one version of it. If you want to distribute, you're going to get 2 terms. So that'll be 9 t to the 1 half times t to the 1 half would be t, right? And then minus, what do we get here? T to the negative 1 half times t to the negative 1 half times t to the 1 half, we get 1, right? That's the same as like the square root of t divided by the square root of t. So there is a really nice cleaned up version of the second derivative. And so now, to answer the question, I'll borrow some space from the next page. The second derivative of y with respect to x, not t, so it gives us the curvature of the smooth curve. Oops, I forgot to put evaluated at. So evaluated at t equals 1. Now I plug in, I get 9 minus 1, which is 8. So if you were talking about particle motion, which is kind of where we're going, I've already mentioned the component vertical velocity vector would be 4. It would be going up, like if you drew the length of the vector or the magnitudes, it would be moving up 4 and only moving right 1. That would be its component velocities. But it's not actually going straight up, and it's not actually going straight to the right. It's moving through a curve. So when you evaluate dy dx and get 4, this ends up being its tangential velocity, which you can kind of appreciate. If we just drew a curve like this, all right, so maybe right here is where it's going up 4, where every one is going to the right. But if it were to somehow break out of the curved path, it would be traveling in this direction by 4, let's say, feet per second. So that's what dy dx does. It gives you the tangential velocity. And if you wanted to add vectors, the way you do it is head to tail. You can actually take that vector, and slide it up here, and now I would have to redraw it. The resultant vector would be, if you connected these two head to tails, it would look something like that. So I didn't really draw them to scale, but that would be the tangential velocity. All right? So if something careened out of its orbit, it would travel in that direction at, in this case, 4 whatever. And this would give you essentially its acceleration as well, if you're looking at the second derivative, which is not just the curvature of the graph then. So you can see kind of how it's going to relate to vectors here coming up shortly. All right, so any questions on that? How to take the first and second derivative? Don't forget, you gotta make sure you remember that. Derivative of what you got, and then divide it by another dx dt for the second derivative. Okay, example 5. Moving right along here. Making good time. May 15th is getting closer every day. Without a calculator, given that x is that and y is that, write an equation for the tangent line to the curve when t equals 3/4. We've been doing this all year long. What do we need for the equation of a tangent line? We need a point and a slope. Okay, so the point is going to be x comma y, which at 3/4 is going to be x of 3/4 comma y of 3/4. So this is kind of what we did yesterday when we were making our little chart for different values of t. Let's go ahead and figure that out first. If I plug into 3/4 for x, I get 4 cosine of 3/4. And if I plug that in for y, I get 3 sine of 3/4. Now you could stop here. These are numeric answers. You could leave it alone like that. But let's review the unit circle. Cosine of 3/4 is what? Negative. Good. Negative square root of 2 over 2. It's in quadrant 2. And then sine of 3/4, also in quadrant 2, is positive square root of 2 over 2. So one of them simplifies a little nicer than the other. The first point is negative 2 square root of 2. And the other one is, I'll just call it 3 square root of 2 halves. All right, so there's the point. Several versions of it. And now we need the slope at the point. Slope at a point. Parametric slope, right? So here we go. I'll do it a little bit differently here. dy dx is what we want. Remember, that's dy dt divided by dx dt, or y prime of t over x prime of t. So what is dy dt if y is 3 sine of t? What's the derivative of 3 sine of t? 3 cosine of t divided by dx dt. The derivative of 4 cosine of t is negative 4 sine of t. Yeah. So you could leave it like that, or you could simplify. That's negative 3/4. And what is cosine over sine? Cotangent of t. So there's kind of a nice cleaned up version of the first derivative. I don't need the second, so now I just evaluated at 3/4. So again, with the right notation, dy dx at 3/4. We get negative 3/4 times cotangent of 3/4. And again, that's a numeric answer, so if you want to leave your slope in that form on a free response, that would be fine. But again, I want to review the unit circle. Pre-Cal took a unit circle quiz today. They were happy to do that. They liked the unit circle. All right, so what is cotangent of 3/4? Tangent and cotangent of any pi-4 reference angle, remember, is some kind of 1. It's either positive or negative 1. This one's going to be negative 1. Good, because we're left and up in quadrant 2. So x is negative, y is positive. So that ends up being positive 3/4. So that would be its tangential velocity, essentially. But we're not really looking at it from that perspective right now. We're just writing the equation of the tangent line. So I'll combine the slope with my point, and I'll do my transitional word. So y equals the y value, 3 square root of 2 halves, plus the slope. Some people are putting minus the slope. It's only minus if your slope is negative. So it's plus the slope, which is 3/4, times x minus the x value, which does make it plus 2 square root of 2. And there's your answer. So nothing really is new. We're just kind of doing it in a new context. Yeah. It's a good point. Y is very, very, very generic. So if you have several things named y, that's okay. If I was to be using the equation of the tangent line, I would probably want to rename it something else. In this case, I kind of agree with you. When in doubt, take precautions. Let's just call it L of x for linearization of x. Yeah. If we were like calling the function, like when we did rectangulars, if we had y equals f of x, and we called the function y, and we were approximating the function, since they said the function is y, then that's when we want to call the tangent line something else, because we don't want to say y of 3.1 is approximated by y of 3.1. See how that can get confusing? If you name your tangent line y also, now that's confusing. Okay? So when in doubt, do give it a distinctive name. It's better to do that than to, just keep your fingers crossed and hope that it's correct. So thank you for bringing that point up. It's a good point. All right, any other comments or questions about example 5? So good so far? So far, so good? All right, example 6. Without a calculator, man, we're not needing our calculator, it looks like today. Find all the points of horizontal and vertical tangency on the graph of this parametric team. So again, this is something that we've done in the past, but we've done it with rectangular equations. So let's kind of map out our strategy. We're going to have horizontal tangent lines when dy dx is equal to what? 0, right? And we're probably going to end up with a ratio. So it would be 0 over non-zero, right? 0 over 5, 0 over 10. 0 over 0, remember, is d and e. And vertical tangents are going to be when dy dx is non-zero over 0. All right, so I guess we're going to need dy dx, yeah? So let's go ahead and find it right here where this stuff is. So dy dx, I'll write it out a little bit differently here again this time. It's y prime of t over x prime of t. So what is y prime of t? Well, it's 2t minus 3. Pretty simple derivatives. And then x prime of t is 2t plus 1. Sweet. Okay, so now we're going to label it. So here I'll say horizontal tangents. And I'll go ahead and write it again. If I hadn't done it up there, for sure I would need it here. Dy dx is equal to 0 over non-zero. So it's essentially when the what is 0? The numerator, right? So if my dy dx is over there, I'll just take the numerator, 2t minus 3, and set it equal to 0. So you're going to get a check for setting the derivative equal to 0 and or setting the numerator equal to 0. Sometimes they let one replace the other. I would recommend doing both of them. And now it's a little linear equation. That's going to be when t equals 3/2. And there are no units on t. Time would be kind of a make sense units, but we're not really talking about units. It's just at that value of t. All right, and then very similar here for the vertical tangents. The vertical tangents. I'm going to write it out again. That's when dy dx is non-zero over 0. Remember, if something makes both the numerator and the denominator 0, we throw it out, because that's going to be a cusp. That's not going to be a vertical tangent. And so that's essentially setting the denominator equal to 0, 2t plus 1 equals 0. And again, you'll get a check for that, and that's when t equals negative 1/2. So at this point, if you did both of them, if you had a t value show up in both calculations, you would throw it out. But we got two distinct t values, and so we want to make sure we answer the question before we walk away. It said to find all the points. Sometimes it might say to find all the points x comma y. Sometimes it might just say find the value of t where you have horizontal and vertical tangents. So if it said to find the points, that could reference the ordered pair. So let's go ahead and find the ordered pair. That's going to be then at, and all I got to do is plug 3/2 back into the x and y. And I'm not going to simplify it too much, but 3/2 squared, when I plug it into x, would be 9/4 plus 3/2. There's the x coordinate. And then the y coordinate is 3/2 squared, which is 9/4 minus 3 times 3/2, which is minus 9/2, and then plus 5. So I'll just leave it like that. If you want to simplify those fractions, I understand it. And then for the vertical tangency, kind of the same thing. This is going to be at, we'll plug a negative 1/2 in, so we get positive 1/4 minus 1/2, and then positive 1/4 plus, it becomes plus 3/2 plus 5. So those would be the XY ordered pairs. And again, all I'm doing is I'm plugging, like we did yesterday, the t values into the x and y equations to get their coordinates. Okay, any questions on that? What's kind of the only thing that's new to kind of have to remember, kind of, sort of? When you take the second derivative, take the derivative of what you have for the first derivative and divide by another dx dt. Okay, divide by another dx dt. Other than that, it's just pretty easy stuff. Okay, parametric arc lengths. We've already had an arc length formula. So let's say that we have something moving through space along a curved path. If you want to figure out the total distance that the particle that's traveling along this curved two-dimensional path travels you're going to need to know, essentially, the length of the curve from t equals a to t equals b, right? It's the same thing. So right now we're just going to call it arc length. It's the length of a parametric curve. But when we switch to vector mode, it's going to end up being the total distance it travels. Okay? Pretty sweet. They have double meaning. So here's the formula. You do have to memorize it. It's very similar to the arc length formula for rectangulars. Let's review that real quick. For rectangular arc length, L, it's going to be the integral from x equals a to x equals b of the square root of 1 plus the derivative f prime of x squared dx. And just kind of worth a note here, when I was grading some of those take-home tests, remember that if it's supposed to be under the radical is covering everything that needs to be covered. And on the other end, if it's not too short, if it's too long, the dx should not be under the radical. You can lose points like that for little careless notations, okay? So there's the rectangular arc length formula again. This one is very similar. It's going to be the integral from a to b. It's still the square root, and we're still squaring a derivative. But it's going to be the x derivative squared plus the y derivative squared, okay? And it kind of looks like the Pythagorean theorem, if you think about it. If you want to figure out what this is, you just take its horizontal component vector and its vertical component vector, and what you're doing is you're essentially finding the hypotenuse, and then you're integrating it from left to right. So x prime squared plus y prime squared. That's another way to write it if you want, from a to b. The square root of x prime of t squared plus y prime of t squared, if you want to do it like that, dt. All right, so another formula to memorize, very similar to rectangular, but different enough that it does require a little bit of, putting it into your hard drive permanently. All right, example 7. Let's go ahead and figure it out. Man, without a calculator, again, the calculator's day off. Find the arc length of the curve given by this and this from t equals 0 to 1. Okay, we got it. We're going to need the derivative of both of those. So let's go ahead and find it off to the side. X prime or x prime of t, whatever you want to call it, it's 2t. And y prime or y prime of t is 12t squared. So now we have the tools that we need to plug in. So the arc length L is going to be the integral from 0 to 1 of the square root of one of them squared plus the other one squared, and then dt outside. So it doesn't really matter which one you plug in. We'll do the x first and we'll do the y second. So it's kind of like alphabetical order. And there's your setup. And that would probably give you 2 checks. And now we just have to evaluate it. And it's said without a calculator. So that means that the integrand is going to clean up to something that we recognize. It should be able to integrate. All right, so let's go ahead and clean it up. 2t squared is 4t squared. And 12t squared is 144 t to the 4th dt. Now, if we started trying to integrate it the way it's sitting right now, you would call that the inside function. Is its derivative on the outside of the radical? Not even close, right? So it's not going to be a power rule on the radical. So we need to kind of think of something else here. What's that? Well, it's part of the function. Yeah, we have to have the square root there. Well, can we? Is the square root of those two things just the square root of the first term plus the square root of the second term? Is that how radicals work? No, you can't do it that way. If they were multiplied, you could take the square root of the product. But you can't just take the square root of each term. So, Noah, you had an idea? What could you do? U sub, is that what you said? Oh, what'd you say? I'm sorry, Noah, what'd you say? Here's what we can do. Is there anything that's common in both terms under the radical? Is that what you said? Okay, that's why I asked you to repeat it. I didn't hear it. Oh, no, just throw it out. Confidence is being wrong at the top of your voice. How about more than a 2t squared? How about a... 4t squared. Yeah. And then that leaves us a 1 plus, now is 4 a factor of 144? Yeah, 32. Let's see, we'll go old school here, divided by 4. That goes in 3 times, that's 12, 24, 36. Man, that felt good. Old school division. T squared. Close parentheses. Now, why is that significant? Now I do have 2 factors, and now I can take the square root of each factor. Well, the first factor, the one that we factored out, which is why I wanted you to say 2 instead of 4, what's the square root of 4t squared? 2t, and then times 1 plus 36t squared. And now I might be able to do it as pattern recognition. Let me come over here, since I'm running out of room, and we'll just start a new column. So the way that we did this in the past, let's set it up. I'm going to bring the 2 out front. He's the writer. I got the integral from 0 to 1 of t times 1 plus 36t squared to the 1/2 power. And now I've got that variable function out front. I can check. What's the derivative of 1 plus 36t squared? 72t to the 1st power. The important part is I generate the variable piece. So I know it's going to work. So the 2 goes along for the ride. If I generate an unwanted 72, I'll have a correction of 1 over 72. And now the t gets packaged back up inside. And I move on to the second part, the rule of integration. It's inside blob to the 1/2, so I'll leave a space. That's blob to the 3/2, and then times 2/3. And then I'll just write the inside function there. So this is where your prowess of 4.4 comes in handy. And now we integrate it from 0 to 1. So we're getting close to being finished. If we simplify any of this, 2/72 is the same as 1/36. And then 2/36 is the same as 1/18. So that's 1 over 18 times 3, which is 54. So however you want to clean up your coefficients, it does simplify to 1/54. And now my beefy eggplant, not eggplant, plum maybe? Purple? You plug in Burple? Yeah, Burple. You're going to get 1 plus 36, so that's 37 to the 3/2. Minus when you plug in the 0, you get 1 to the 3/2. And I'm going to stop right there. 37 to 3/2 is not a real nice number. Square root of 37 cubed. 1 to the 3/2 is just 1. But anyway, there's an exact answer. So yeah, it does work. That's the length of the calculator. I read the word calculator as I was talking. So without a calculator, that's the length of the curve. Whew. Happy National Agriculture Day, everybody. Yeah. Go plow a field or slaughter a hog or something today. Celebrate. All right. Any questions or comments or good, clean jokes at this point before we move on? Okay. Let's move on. It's time to revisit particle motion. I've been kind of alluding to this. Horizontal and vertical velocity component vectors. So everything we've been doing right now has been strictly parametric. When we pair them up, we get vector calculus, okay? And just real quickly here, a vector, this is a vector. It has 2 components. It has a tail, first of all, and a head. The head is the arrow part. But it does have 2 main parts. It has a direction, and I heard that over there. The direction is the way the arrow is pointing. So this one is going that-a-way, to be very specific. This one's going that-a-way. And then it has a magnitude. There's lots of words for the magnitude. You can call it the magnitude. You can call it the length of the vector. Sometimes it's even called the norm of the vector. Okay? But that would be this right here. So if we call the vector, we give it a name. Let's call it V. We usually put an arrow over it. Textbooks maybe put a double-headed arrow over it. I'm kind of lazy, so I'll just do like a one-headed arrow on it. So we can call that vector V. And then the magnitude of the vector is written in one of two ways. It's written like that with absolute values around it, but it's not really the absolute value, so sometimes it's written in double bars. And that just means the length of the vector. Okay? They mean the same thing. Okay, sweet. So when you add vectors, and I've kind of mentioned this already. So let's say you have one vector that is going this way and another vector that's going that way. Those would be your component vectors. You have a vertical, hang on, it's not quite, there we go. You have a vertical vector and a horizontal vector. If you want to figure out what the tangential velocity is, the direction, you have to add the vectors, and you always add vectors head to tail, okay? And these are tail to tail. So what you would do is you can either reproduce that vector over here, or you can reproduce the other vector over here. So sometimes they tell you to draw a quadrilateral, and then if you draw the diagonal of your quadrilateral, you get the resultant vector. Okay? Did I do it wrong? Yeah. I did it wrong. Yeah, okay. Because I drew too many things. So let's slide this one here. There we go. So here would be your resultant vector. Yeah, and we usually call that R. So what we have is the particle is actually moving in that direction along a curved path. And if you wanted to break it down, this would be its vertical component vector, which we're going to call y prime of t, the vector. And then this would be its horizontal component vector, which we call x prime of t, with a little vector over it. Okay? So it's kind of like the Pythagorean theorem. So it's moving through a curved space. The resultant vector, as we already saw, would be its tangential. If it broke out of that curve, it would be traveling in that direction, and then the length would be the speed, essentially, which it's traveling in that direction. So there's a real quick overview of vectors by using head-to-tail arrows. I don't like to draw the quadrilaterals because it messes me up, as you saw. But yeah, slide one or the other, doesn't matter which one, and then connect head to the tail. All right, so here we go. Horizontal and vertical velocity component vectors. X prime of t, of course, is dx dt. That's the rate at which it's moving left or right. And y prime of t, or dy dt, is the rate at which it's moving up or down. So here are the vectors. S is the position vector. And it's basically x of t comma y of t. It's typically written not in parentheses, but rather angled parentheses, which we call chevrons. It's the same thing from like the military insignias. These are just turned sideways. So we call those chevrons. Now, a lot of the times, the position is not written in chevrons. It's written as an ordered pair. But either one is acceptable, okay? Similarly, the velocity vector, which we're going to call v with the arrow over it, it's the derivative of the positions, and you're just listing them x comma y. So it can be written again in chevrons, or even sometimes it's written without chevrons. There's a lot of like duality of notation here. I like to use the chevrons just because it's kind of a novel thing. And then the acceleration vector is going to be the derivative of the velocity components, or the second derivative of the position components. And once again, it could be written with chevrons or with parentheses, okay? So the main thing to remember is we are drawing little arrows over our vector names, and we're listing them essentially as ordered pairs, okay? dy dx, we've already talked about that. That's the rate of change of y with respect to x. It's still the slope of the tangent line. It's your tangential velocity, if you want to add that in there. That is your tangential velocity. If you were to break out of the curve, and then d squared y over dx squared is still your acceleration. It's still the concavity of the curve, but it gives you the acceleration. Okay, so as we drew up here, if you want to figure out the speed of the particle at any given moment, you need to know what the length is of the resultant vector, okay? And it is going to be a Pythagorean theorem kind of thing. So you would need to know the length of the horizontal vector, the length of the vertical vector, and then the hypotenuse would just be the square root of the sum of their squares, right? So let's jump down here. Where are we? Okay. The norm of the resultant vector, which I said you can use in single or double bars, is nothing more than the square root of x prime squared plus y prime squared. It's the Pythagorean theorem. Okay? This gives you the speed of the particle. Now think back to particle motion in 2 dimensions. When I integrate the speed function from A to B, which back then the speed function was the absolute value of v of t, that's when we had no cancellation. That gave us the area under the curve. Was that the distance traveled or the displacement? Yeah, this was the total distance traveled. The total distance traveled. Because we made everything positive first by nuking it with the absolute value. Whenever you integrate speed, and this is kind of important to remember, it'll carry through. When you integrate speed, you get the total distance traveled. Well, if this is the speed of our particle in 2-dimensional space, what happens if I integrate that? I get the arc length, which is also the total distance traveled along the curve. So they're one and the same. And this is what we just memorized. It's still going to be the arc length, but because it's the integration of the speed, it also gives you the total distance traveled. Okay, and that's what I put down there. Remember that gives you the total distance traveled. All right. Good stuff. The chart is nice. It's nice to read, but it kind of makes more sense once we start using it. So let's go ahead and do that. Example 8. We're on page 4 or 5. We'll probably finish tomorrow. Hey, look, no calculator. Our calculators are like Gorell today, still on spring break. We're not using them. A particle moves in the xy plane. Okay, so that right there is your key to realize you're going to be doing vector calculus or parametric calculus. When you have something moving on a horizontal line or something moving on a vertical line, that is old particle motion. That's one-dimensional. When it's moving through the xy plane along either a smooth curve or just on the xy plane, that's two-dimensional. All right, so that's going to be vector/parametric. So that at any time greater than or equal to 0, that's kind of important, the position of the particle is given by these two parametric equations. Part A, find the velocity vector at t equals 1. That's part A. All right, so how are we going to find the velocity vector? Well, let's name it first, v of t, and we'll give it the little velocity vector sign with the arrow above the v. It's going to be chevron x prime of t, with the little vector there, and y prime of t. So we could do that in one step, okay? So if x is t cubed plus 4t squared, its derivative is 3t squared plus 8t. Let me rewrite that. 3t squared plus 8t, comma, and then y prime is 4t cubed minus 3t squared. So just simple little power rules. So there is your velocity vector. We list it as an ordered pair. And now, at 1, we can go back to function notation. The velocity vector evaluated at 1, we just plug it in. So 3 plus 8 is 11, and 4 minus 3 is 1. So if you were interested in what that looked like, you can always kind of draw your x and y axis, and you would go out 11 units and up 1 unit, and this would be your horizontal vector, and I'll just draw it out here because it's already head to tail that way. That would be your vertical component vector. So at this moment in time, this particle is moving through a curved path, and most of the energy is for horizontal motion. Now, what direction is it actually traveling? Well, that would be this. This is your resultant vector right there. It's actually traveling along something in that direction, and if I want to figure out what the speed is, which is part B, what's the speed of the particle at 1? I need to figure out the length of that resultant vector. And how do I do that? Pythagorean theorem, right? That's it. So here you go. Part B, you're going to say, I like to use the double ones because, again, it's kind of novel. And it does separate it from the absolute value because we're talking about vectors instead of just up here the absolute value of velocity. So it's going to be the square root of 11 squared plus 1 squared. So if you think about it geometrically, you don't have to worry about memorizing formulas. You're like, oh, it's the Pythagorean theorem. The square root of the sum of the square of the two component sides. And so that ends up being 120, square root of 122. So if that thing were to break out of its curved path movement, it would be traveling in the direction of the pink arrow at a square root of 122 units of length per units of time. All right, part C, we need the acceleration vector at that time. Okay, so let's go ahead and find the acceleration vector first. We'll call it a vector of t, and I'll just come over here and say it's going to be x double prime of t, comma, y double prime of t. And I have the derivative already in the velocity vector, so we'll just take the derivative of the velocity vector's components. That's 6t plus 8 and 12t squared minus 6t. So there's your acceleration variable vector. And now using the correct notation at 1, we just plug it in. 6 plus 8 is 14. 12 minus 6 is 6. Now, you're probably not going to be asked to find the norm of the acceleration vector because, as far as I know, it doesn't have like a practical name given to it, like speed is the length of the velocity vector. I don't know what you would call the length of the acceleration vector, but you could. You could just as easily use the Pythagorean theorem there and get the magnitude or the length of the acceleration vector. Okay, so we're listing the vectors as ordered pairs. And that's it. That takes care of part A. What's nice about vectors is as long as they keep the same length and they're pointing in the same direction, you could draw them anywhere in space. So I drew them at the origin. That's kind of putting it into standard form. But I could have had the x and y axis right there. And as long as I'm drawing those horizontal and vertical vectors, you know, again, same length, parallel to these, it's exactly the same. So you can move this around anywhere in space to do the math. Okay, so I might as well just put it at the origin. Cool. Now, if you wanted to see what the path actually is, it says no calculator. This kind of makes it a little bit more gratifying on the back end of it. Let's go ahead and see what the curve looks like. This would be like what we just did would be kind of like watching the movie by reading the subtitles, and our eyes are closed. Well, no, not our eyes are closed. We don't know what the movie is. We're just reading the subtitles. But now we can actually come back and see what the movie is. We get to see the picture. That was a horrible analogy. Forget I ever said that. Reading the script. There you go. I knew there was a way to do that. Reading the script versus seeing the movie. What's going to work? Teamwork. Very good. So I go back to parametric mode, and we'll type in the positions, t cubed plus 4t squared. T cubed plus 4t squared. And then for the y, t to the fourth minus t cubed. Okay, t to the fourth minus t cubed. And we'll go to our window. 0 to 2 pi is default. I'm just going to hit, let's see, zoom 6. Actually, there you go, zoom 6. All right, so let me adjust my window now. How about -1 to 20? That looks good. And then I don't need to go that far down. How about -5 to 15? See if that. Okay, so there you go. And we were at t equals 1. So if you hit the trace button, you could type in a 1, and you can see that it's right there. So that is where we're talking about. And so if you notice, the graph is pretty flat there. So at this point, it's moving along this curved path, but it's going right 11 units at that point for every 1 it's going up. If you were to draw the tangent line, then that would be essentially the direction it would be heading if it broke off of that curved path at that moment. That would be dy dx. And then the speed at which it would travel tangentially if it broke out of the curve would be the square root of 122. Okay? So that's what we're doing. Very satisfying now to see the picture. Great movie. Okay? All right, comments or questions so far? All right, let's see if we can squeeze one more in before we take a stand, and that might conclude the whole lesson. All right, no calculator again. All right. There we go. A particle moves in the xy plane. There is your two-dimensional parametric / vector alert. So that x is that and y is that, where we're going from 0 to 2 pi. Okay, so now they gave us an interval to work in for t. Find the first and second derivative. And these examples here are kind of based on free response questions. Okay, so this is very similar to what you might be asked to do on a free response. All right, dy dx, notation. So dy dx is y prime of t over x prime of t. I like to do it like that instead of dy dx over dx dt because it doesn't look like a complex fraction. So you can either take the derivative over here separately and then plug it in, or just take the derivative for the first time in the answer. So what would be the derivative of y prime? Or what would be y prime, sorry? 0 minus 2 cosine? The only good thing about having it component-wise is if you ever needed to come back and find just like the vertical velocity, you'll have it listed there and labeled there. It's kind of nice. And if you ever needed to come back and find the horizontal velocity, you have it right there. So I'll go ahead and do that. So the x prime is 4 sine of t, and so that goes in the bottom, 4 sine of t. Just remember, you're putting the y's in the top and not the x's in the top. The x is usually listed first, but y goes in the top. If you wanted to, again, simplify that, that's negative 1/2. Cosine over sine is cotangent of t. So again, notice the difference. My t for cotangent is straight. My t for the variable has a little curve on it. It's kind of nice to have a little differentiation. Did it ask us to evaluate it at a specific point? No. So if this were a free response, I would probably stop right there, negative 2 cosine over 4 sine. But I would maybe simplify it if I had to evaluate it. All right, so now it's time for the second derivative. The second derivative of y with respect to x. Let's go ahead and write it out. It's going to be the derivative with respect to t of dy dx. So the derivative with respect to t of what we just found, and we divide it by another what? Dx dt or x prime of t, whatever you want to call it. So you don't actually have to write that out. You don't have to write that out. You just have to do that. Writing it out maybe helps you remember to do it. All right, so this is where simplifying your derivative could pay off. So you don't have to use the Hody-High rule. So negative 1/2 goes along for the ride. What is the derivative of cotangent? Yeah, negative cosecant squared. Yeah, negative cosecant squared. So there is the derivative of what we started, or what we got for dy dx. That is not the answer, though. We must now divide that by another dx dt, which you can see right there was 4 sine of t, or you can come back over here and see it's 4 sine of t. And again, that's the one part that many students, not y'all, forget to do. And if this were a free response, there would be no real reason to simplify that, but we train for both. So a negative times a negative is positive. A half divided by a fourth is an eighth, right? And if I bring this sign to the top, it becomes another factor of cosecant in the numerator, and I can call it cosecant cubed. All right, so after the stand, we'll go ahead and finish up part B, and we'll be done.
Thank you.
Okay.
Attention, junior.
Go ahead and read B on your own while you're listening to Ms. Shriver. Read B on your own.
The deadline is quickly approaching. Don't miss out on this once-in-a-lifetime opportunity. Also, we will have some visitors this week in the College and Career Center. Tomorrow, we will have the University of Incarnate Word at 8:50 a.m. and St. Mary's University at 1:35 p.m. Thursday, we will have Wayland Baptist University at 1:15 p.m. Please stop by if you'd like to attend any of these. Also, I do have the prom visitor permission slips available in the back office or in the front office. So if you're going to have a guest that is not a student here at New Braunfels High School come to prom with you, you need to fill out one of these forms. Thank you.
Okay, so this is a really good question because you have to think a little bit. Once you see how it's done, though, then when you see it again, you don't have to think so much. The path of the particle intersects the x-axis twice. Write an expression that represents the total distance traveled by the particle between the two x-intercepts. Do not evaluate. Okay, I won't. So we're trying to find the arc length, essentially, right? The total distance traveled. But the particle intersects the x-axis twice. So I just drew a random curve. It's not necessarily what the curve looks like, but I drew it across the x-axis twice. We need to figure out the t values where that happens, and we need to use the information that's already been given. So anytime something crosses the x-axis, what do you know about its either x or y coordinates? Good. You know that the y is equal to 0. That's what's important. If it were crossing the y-axis, you know x is equal to 0. That gives you something to work with. We need to set y of t equal to 0. All right, so y of t was up here. It was 1 minus 2 sine of t. So without tunnel vision, you wouldn't have to scroll up and down. 1 minus 2 sine of t. So you'd probably get a check just for setting y of t equal to 0. If it's a non-calculator problem, it's going to end up being a unit circle ratio that you're expected to know. So sine of t is equal to positive 1/2, and this is not inverse sine the function, this is solving. So where does sine equal positive 1/2? Between 0, remember, and 2 pi. That's within one positive rotation. Yeah, it would be there and over here, pi 6 and 5 pi 6. Yeah. So knowing the unit circle, still very, very important. So those are my two t values. And now all I have to do is set up and don't evaluate the distance it travels. So here we go. You can use d for distance if you want instead of L. It's going to be the sum from pi 6 to 5 pi 6 of the square root of x prime squared plus y prime squared, or dy dt squared, dt. And now again with tunnel vision, I have to come all the way back up here. X prime was 4 sine of t, so 4 sine of t. And y prime back up here was negative 2 cosine of t. Negative 2 cosine of t. And then my radical covers the squared but not the dt. I have the dt on it. I've labeled it d. I've got everything there. I don't need parentheses around the radicand because the radical does the job for me. Do I need to simplify it any further than that if this were a free response? No. And notice we've got the parentheses containing the 4 and the negative 2 under the radical, so that's fine. You could stop right there. If you irresistibly wanted to keep going, don't. Okay? Don't. Just maybe memorize what it was. When you get done with the test, then simplify it. But it would become 16 sine squared of t and then plus 4 cosine squared of t. So again, if you had had the right answer up above, but you messed up the square, like you called it minus 4 cosine of t, hey, free lunches. You would get it wrong now. You would get it wrong. All right, so anyway, there you go. We finished this section. That's parametric derivatives and parametric introduction. The worksheet, I don't remember exactly how long it is, but we can make it due Thursday. How about that? That gives you an extra day to put it off. But yeah. So the worksheet will be due on Thursday. And tomorrow we'll just jump right into 7.